Hello, everyone, and welcome back to another geostats lecture video. And in this lecture video, I actually want to wrap up this section by talking about this idea of multiple hypothesis testing. Or sometimes you might see this called multiple comparison testing. Right, and basically this has to do specifically with these LISAs because of what the p-value actually means, sort of aside from, rejecting the null hypothesis, and what it means to be doing multiple of these things, right? Because again, with the global Moran's I, right, we had one test statistic, we had one p-value. With the test for normality for the data set, right, we had one test statistic, we had one p-value. With chi-square, we had one test statistic, we had one p-value. Now with these LISAs, right, we have potentially hundreds of test statistics and potentially hundreds of p-values, right? Because that's what a LISA does, right? You get a test statistic for each polygon, and then you get the associated p-value for that polygon. So you could potentially have hundreds of these things instead of just one. And so you run into what is called multiple hypothesis testing. And what you have to remember here, right, is that a p-value, right, a p-value of 0.05 means that we reject the null hypothesis right, with a confidence of 95%, right? That's what this 0.05 means, right? Is that our value is expected to be this value or greater 5% of the time. So we're rejecting that null hypothesis with a confidence of 95%. But think about what that actually means for a second, right? That means that 5% of the time, right, 0.05, right, 5% of the time, we would be rejecting the null hypothesis when it's actually true, right? It's called a false discovery or a false positive, right? We're rejecting the null hypothesis incorrectly, right? It's false. We shouldn't actually be doing that about 5% of the time. So you can imagine, right, if we're running 100 polygons, right, we're calculating 100 p-values, we would expect, just based on 0.05, right, that 5% of the time when we're rejecting the null hypothesis, it's actually wrong. Okay? Let me repeat that because this is kind of important. When we're doing multiple test statistics and multiple p-values, like we do in the case of these LISAs, right, we would expect with some proportion that we would actually be rejecting the null hypothesis incorrectly, simply because we just have so many of these test statistics. And our confidence of 95% is saying, hey, 5% of the time, we're going to be wrong. And we're okay with that when we're only doing one test. When we're doing 100 tests, well, now we can be fairly confident that we actually have at least one instance where we have falsely rejected the null hypothesis. Okay, so that's the idea of multiple hypothesis testing, is that when we're doing this thing, hundreds of times, that the 0.05 p-value just simply isn't going to cut it, right? We're going to be rejecting the null hypothesis incorrectly too often for the number of times that we're actually doing this thing. So what we need to do is we need to actually account for this. We need to adjust, right? Adjust the p-value, right? And so the first way that we can do this is called Bonferroni. Right, so the Bonferroni method of adjusting the p-value so that we are far more than our statistical significance, right? The alpha threshold, the cutoff, right, is going to be accounting for the fact that, hey, we're doing this 100 times, 1,000 times, 50 times, whatever, is to simply use the Bonferroni method, which divides critical P by the number of tests. Right, so if we are doing this on a data set of 25, example. So if we're doing this on a data set of 25 observations, right, we have 25 polygons, right? Bonferroni would simply say, take 0.05, divide it by 25, right? And that's your new alpha, right? That whatever you get, that is the new critical threshold that you're going to use to determine whether or not you reject the null hypothesis. Right? You simply take your critical P, so 0.05, you divide it by the number of tests you're running, which is the number of polygons that you have, and that's your new critical threshold. Okay? Really simple. It's widely used. One issue, right, one criticism of Bonferroni that you will often hear is that it's too conservative. Right, it's too conservative. Dividing by the number of tests, right, especially if you have a lot of tests, right, you're making your critical threshold a lot smaller. So you actually may be going too far, right? You may now be going the other way, where you are not rejecting the null hypothesis when you should be. Okay? Because the problem is we're rejecting it when we shouldn't, right? So Bonferroni says, well, we'll just divide the critical P, right, the critical threshold, by the number of tests, and that'll be our new critical threshold. Well, some people argue that that's too conservative, right? Now we're going too far the other way, and we're not rejecting it when we probably should be. So there is an alternative method, and it's called the false discovery rate, or FDR. So the false discovery rate, the equation is a little bit more complicated, so we're not actually going to go through that here. But the idea is that this is a less conservative method. Which accounts for false positives. Right, and again, a false positive is when you do something and you shouldn't have done it. Right, that's a false positive. So hopefully that makes sense. Again, false discovery rate, I'm not expecting you to really know much more than the fact that it's a good alternative to Bonferroni, and that Bonferroni is really just dividing your critical P by the number of tests, and that a lot of people argue that it's too conservative. So hopefully that makes sense. And as always, please reach out. Thank you.